Okay, so let me introduce Kyungyong Lee. He's professor in the Kookmin University in Seoul, South Korea. And well, he's a senior researcher in distributed systems. He follows a similar career that our research group, because he started doing peer-to-peer in Florida with Renato Figueiredo and doing very interesting things in large-scale distributed systems. And then when peer-to-peer declined, he also, like us, he moved to cloud computing. He has worked also in the industry, in Amazon, in AWS Cloud, but also in Palo Alto, in HP Labs. And later on, he moved to Korea as professor, and now he has a very interesting research group with topics that we are very interested and we should really attend, because many of our research topics are overlapping with him. The title is Towards Autonomically Evolving Cloud Computing Services. And let's see what you explain. We are really interested.
Thanks for introduction, Pedro. So nice to meet you here. So I'm Kyungyong Lee. And first of all, thank you very much for having me an opportunity to presentation in the here. So just to give you a little bit background how I contact Pedro and came to URB. So I'm not sure whether you're some other in department and other like some research area, but in Korea, government is like having a lot of effort for collaboration with some overseas country, and EU is one of the biggest the government effort is going on. So from that perspective, actually I knew that the research outcomes from Pedro quite a lot, and also Mark Sanchez, right? So I know his work, of course, because reading lots of papers, actually your groups are really making a lot of like good research outcomes. So I knew there are some nice groups in Spain here. So from that point, I thought about, well, actually we didn't have any previous contact, but just I thought about if I'm going to collaborate with some EU country, which I want to be a good candidate. Because I thought, well, this guy is doing great in the research, and I just sent an email, and he really graciously accepted me as a PhD here. So that's why I'm here. And today, so I'm gonna talk about some of my recent research topics that I think that's gonna be really helpful for you and myself. So to have some collaboration at the further research in the future. So let's start. So let's start from the domain of my research. So these days, the artificial intelligence and with AI and deep learning is really widely used in many fields, like some autonomous driving, language translation, and also object detection. They're really widely used with some many factors from like new hardware, new algorithmic development, and also platform development, especially for the distributed environment perspective. From the perspective of deep learning and application development, they are mainly divided into two parts. One is training, one is inference. Two things that train, which really models the input the patterns to some specific model. It requires a large compute power, which requires very high throughput, and it generally happens in burst ways, which means that if the training happens, high throughput computer or high resource usage is required, kind of like short period of time, like a week or some even for a month. Different from train, the inference, it really interacts with the end user's request, and it provides trained model, the outcome to the end user. So because of that, it needs to process users' request elastically as like users' request changes. And different from train, which requires higher throughput, for inference, it generally requires very short latency for successful service. And to meet such demands of artificial intelligence, cloud computing is very good platform as an AI development platform. So first of all, most of you might know, the auto scaling in cloud computing is very beneficial for both for training and inference, because it requires very like demanding or changing access pattern. And like for DNA training, for occasional execution of DNA training, elastic scaling and also DNA inference for that to handle dynamic requests. But that is very similar to a general web request. That automatic scaling is very helpful. And on top of that, there is some, but many people, I think, in our school, and there's most of the researchers in Korea also, for doing some deep learning related stuff, we generally use GPUs for training or for inference, but it is very expensive compared to just buying one. So even if that cloud computing is like known for its cheap, like some efficient usage, but it's still expensive. So that is one reason people do not use that, and usually quite often. So, but there is some another way to use those cloud resources in a very cheap manner by using spot instances. So in some cases, comparing to the like some on-demand regular prices, sometimes it had like over 80 to 90% of the reduction comparing to that the on-demand price. However, for the spot instance, the sudden interruption can always happen. So in this scenario, so if we wanted to deploy AI applications or development platform on cloud, is it generally easy, or what we have to consider whenever we like want to deploy AI application on cloud? First of all, I have several columns. The first of all, for training, we need to decide which hardware we can use on cloud. Generally, people mostly use GPU these days, but however, from the cloud perspective, new hardware is keep releasing, like such as Google TPU. Also recently, where AWS Trainium was released, and people can use that just for training purpose. And after choosing that hardware, we can set up the training environment. It can simply use a single GPU, or you can use multiple GPUs in a parallel environment setup, or we can use a distributed training setup. Not just for training, just for inference perspective, there are also many options so that users can use on cloud, such as for the workload characteristics of inference that is user-facing. People can use CPU, either by Intel or ARM. For the ARM CPU perspective, these days the cloud vendors are really releasing ARM servers very easy to use way to the end user, so it's very accessible. And also for the NPU perspective, AWS recently released Inferentia just for the inference task. And the serverless computing also can be one good way of serving inference job because it is really user-facing and it really that dynamic user access pattern. And also from not the cloud perspective, but at the model optimization perspective, there are many other like model optimizer like TVM, Onyx, and Optimino. And also there are very, very different models like large language models, GNN, RNN, CNN, etc. And also there are many hyperparameters that users have to set up. Then my question is, our research lab is what we are doing is that there are really many ways of make dimension of choices that the users have to choose. And let me give you some brief introduction or to brief our experiment result regarding the performance diversity when choosing some different environment. The first one is train. So in the train, we have like two models, Linear 5 and AlexNet. There is two different models with some different sizes. And we train those models using 4 different GPUs provided in AWS. And the bar says that the training time. And what we could see was that the training latency of 2 different models is very different, which means very different. And there is no single GPU that works the best for across all both of that models. So for example, NVIDIA T4 works best for the Linear 5, and VBAC, that is P3 in AWS, it works best for AlexNet. So which means that as we choose different GPUs, the performance can vary greatly across different models. Next one is about the inference perspective. For the inference, we use the AWS Inferentia, that is like use the NPU devices specifically for DNA inference. And if we use the like AWS Inferentia for Reginet 50, I think the last 4th bar is for performance of that AWS inferentia. And the Regina 50 shows the best performance for the inferentia. However, when it comes to DenseNet 121, that is a little different model. The inferentia showed the worst performance comparing to any other like GPU and CPUs, which means that people generally these days think that the AWS inferentia is just for inference, and if I use it, I might get best performance. However, it is not true. So if people do not really like take care about its optimization or very well tuning, the performance is not such good. So that's what you could see. And from the cost perspective, I'm showing you about some heat map of spot instance prices of like some AWS GPU and general type. And in the middle, there is some GPU instance type. And this black part means that there is really no cost reduction from using spot instances, while the lighter part seems like higher cost reduction, which is like over 70 or 80% of reduction is possible when using spot instances. For compute memory, IO in general, which is not having any GPUs, they can have a lot of some cost gain by using spot instances, but not for GPU instances. GPU is changing quite a lot based on its availability and cost reduction perspective. And so availability was very different for across all the different models, different GPUs, different instance types. So from those observations, what we think is that for AI algorithm developers who is not generally system developers or cloud expert, it can be very challenging for them to build and maintain an optimal environment on cloud. So it should be autonomically evolving cloud system so that by providing some higher degree of abstraction and higher degree of that access layer to algorithm developers by hiding some very diverse hardware and service orchestration configurations. So that's the where my research lab is like actively now working on. So from the perspective, my lab is currently running a project called ACE AI, which is acronym for Autonomic Cloud Environment for AI. So ACE AI this system is mainly composed of three parts: ACE train, ACE cost, and ACE inference. For the ACE train part, and so I'm gonna tell you about my group's recent research work in each domains one by one, which is still ongoing. But for the ACE train part, I'm gonna tell you about like Prophet that does like prediction of a CNN training time on various GPUs. For ACE cost, which does that cost optimization on the cloud for AI jobs, which means called Spot Lake, for Spot Instance Dataset Archival Service, and for the ACE inference, which does some inference on the cloud. So let's start from a Prophet of ACE train. So GPU is widely used for deep learning model training, and cloud GPUs can be a very good choice for many of the DNA training jobs. And the GPU devices are quite evolving very fast. There are many new GPU devices that keep releasing, and they are becoming available through cloud services like this one shows over from Amazon with some various devices. But here, so what we wanted to solve from this project was that using this many type of GPU devices, if we can predict the training time of any single model, can it be really helpful? So I think we think so, because first of all, assuming that a user has its own DNA training model or DNA training code, and if one can after running like training job, and if one can expect or one can predict the training time on the other GPU devices, they can like think about migrating to other GPU devices easily. And also from the GPU cluster or cloud vendor perspective, if they the service provider can know how DNA training performance can be different across all the different devices, they can take that information for their optimal resource scheduling. But one step further, there is something called like network architecture search in DNN, just for better some accuracy and performance. And combining the network architecture search with some DNN training time, and whenever we do find out for network architecture search, not just for that accuracy, but you can also think about this training time and also resource efficiency, also things like that. So I think we think it's going to be very helpful for the DNN time prediction. So because of that, there are some other previous work which it tries to do DNN training time prediction, and I think this is the first work in the domain of DNN training time prediction, which is called Paleo, presented in 2017. And since then, there are other lots of work, but this was the very first work, so I'm citing it here. So in this work, what they do is that the authors really like analyze the model's internal architecture, so each layers and activation functions and every different layer. And then based on that, it builds a model with considering all the hardware details. It builds a model about how its computation time is going to look like for a different type of hardware, like such as GPU with some different flops and memory size or some things like that. Also, what about the communication cost? And after doing the computation and communication cost, it predicts execution time, and it works pretty well. So it by simply referencing this internal model's internal architecture. But here, my group, but in this work, they are not really targeting that cloud environment. They are just thinking about any general GPU environment. But my group is actually working on mostly on some cloud environment and cloud environment setup. And we thought about some limitations of the previous training time predictor from the like confidentiality, prediction accuracy, and compatibility. First one is about confidentiality. Here, what confidentiality means is that in cloud, so we assumed that we want a cloud system can provide optimal training environment to users. Not it should be done by end user, but the optimal resource selection should be conducted by cloud vendor. And to do that, cloud vendor should be able to access those users' source code or internal architecture to predict training time on multiple GPUs, which is not likely to happen because anyway, in most cases, in cloud computing environment, resource provider and resource user, they are two separate entities. And in most cases, cloud users are not really they do not want to expose their application source code or application asset to the cloud vendors, which means that if you want to do this type of like other like previous work, which should export the internal network architecture, it cannot be really applied to current existing cloud environment because all the internal details should be provided to the cloud vendor so that they can provide some other optimal environment based on usage prediction. The first one is about the confidentiality. Next one is about prediction accuracy. Not just for the Paleo, but in the other way, there are some other many work who actually do some prediction for different batch sizes, but the prediction accuracy was not that great. There was compatibility with some compatibility means as that DNN model gets evolving and new layer and new operators are coming out. The previous approach could not really handle a new type of approach that is not new type of operations that was not involved in the training. So we wanted to solve this problem. And to do that, we proposed Prophet, which is profiling-based CNN performance model for GPU instances. So in this approach, different from the previous approach, which uses model's internal architecture, while it's very detailed layer information, we decided to use profiling information to predict training latency in some other GPU devices. So in our proposed approach, we use some profiling result that is provided by training platform. So this shows one example of that profiling output. So if a user programs its own DNA model and they do training on one single GPU, and then they extract that operation features as some profiling feature. And then, so for example, if a TensorFlow profiler, if we use it, it gives out this type of information. The operation name, it's very detailed layer name, also output and input tensor size, and also some memory and time and things like that. And this profiling information is really very detailed, and it actually contains the entire information that is actually embedded in that model architecture. But our goal was to hide as much information as possible from the user, and the cloud, we wanted that cloud vendor can access, or cloud the resource provider can access that very limited information. So to achieve that, we using some operation-wise aggregated time information. So this like center part, that is very like detailed information, and without using that, we just drop all of them, and we just do aggregating based on operation name. So for example, the conv2d value and max pool, that is some operation name, and we aggregate by conv2d, and we get some total aggregated time and value and max pool and things like that. And we use only those information to predict that training time on multiple and on GPUs on cloud. So this is how we achieve that confidentiality. And then using those using the information about the profiling result, the prediction model of Prophet is composed of three main parts: operation clustering, cross GPU modeling, and batch size predict. Let's see one by one briefly. First one is about DNA operation name clustering. So in the previous slide of using that profiling result as a prediction to hide model's internal architecture, there is one issue for that profile, the operation name. The operation name is like generally used by, set by the vendor, the platform developer. But in some cases, there are some a little bit of like some variant, like some there is value, that is one activation function. There is also value 6, that is like slightly different activation function from value, but they are very similar. But their name is actually different. Because the name is different, they are actually regarded as some different features, and it really could like drop the prediction accuracy in our model. So in the like DNA operation name clustering, what we have done is that based on all the operation name, we measured some like name distance between two different all the models, and based on that name distance. So if the name distance is very similar, like value 6 or average per max pool, that is very close to in the text similarity, we cluster them as a single same feature, and we just use it in our prediction model. So after applying this one, you could see that. So for some cases, this actually graph shows two cases. One with models that contains many unique operation names. In this case, we could see a lot of some performance gain. However, models, if it does not use any some specific or some unique name, if they are just using common names, the clustering does not really help. So it did not get that much performance improvement. However, the performance degradation was not happening. So in most cases, with that newly the unique operation name, you could get a lot of some performance gain. So this is what we could do by doing some name clustering. And next one is about anchor target GPU latency prediction. So in here, so our major goal is that, so assuming that a user has run a training on a anchor GPU, like some T4. So a user has like training on T4, and he wanted to predict the training time on VBAC or ABAC, which they did not use. So to achieve this goal, how are we going to define input and output features for that training time rate prediction? So in here, in the anchor target GPU relationship prediction mechanism, we define the X as some input feature as a profiling result at an anchor instance, like for T4, we insert that some abstracted profiling information as an input, and also that to build some output, we do target GPU instance latency as some output. And best after having them, we tried various other machine learning algorithm, and we find out that some medium bagging ensemble showed the best performance in here. So we define the anchor and target by using some profiling result and the training time as our feature. And next, we also tried to model the training latency as the batch size changes. So in general, whenever we do a DNA training, if the batch size gets larger, the training time gets decreased. The entire training time gets decreased. And in the previous approach, people generally use some very simple linear regression model that wasn't very accurate. So we could see from other papers, we could see that the linear model was not that accurate in the different batch size prediction. So we do some like propose a min-max scalar with some normalization to make that batch size prediction accurate across very like different models. So in here, we define minimum and maximum batch size, and we normalize based on the maximum batch size latency as 1.0 and with minimum. And then in that time range, we propose to use like second order polynomial regressor. And then based on that, we do predict the batch size prediction, training latency. So after combining all the name clustering and anchor target modeling and also batch predictor, we did some experiment using all the GPUs on the AWS cloud with some all those shown in here with some those specs. And also all the CNN models of Virgili, ResNet, and all these models with the different batch sizes, with the different input, with some TensorFlow. And this one shows that graph of how the performance looks like. So in here, what it means is that when each one at the title caption, it shows the different anchor instance type, and this one shows that the graph of y equal x. This means the perfect prediction. So the dot close to this line means that the prediction is very accurate. So based on our observation across 4 different GPU types, you could see that we can really accurately predict that training time across different GPUs. And also we was compared with other state-of-the-art approach, the Paleo that was in 2017. We could see that for few models that was common in the both approach, we could see a lot of some gain in the performance prediction accuracy. Also, ML predict that also does some prediction for the different batch sizes, and we could see a lot of like some performance gain also. And I think from this context, the habitat, which was proposed in Unix ATC in 2021, I think that was the most recent one. And from comparing to that, you could also see some performance improvement comparing to that previous approach. And we also did another type of experiment. So in this experiment, what we have done was that, so at the time of our writing, we used the 4 GPUs, M60, T4, K80, and VBAC that was available only on AWS. But in the meantime, there was some another new type of GPUs released, like AWS G5 with A10, and IBM AC1 with P100. And we were curious, can we apply all the models that we used in the older generation of GPUs and with all the models? Is it going to be applicable to newly released GPU? And we did that after building a model. And we could see that the prediction accuracy was quite high. Like for some cases, in most of the cases, error rate is like less than 10%, which is quite accurate compared to any other like previous model. So we could see some general prediction accuracy across all the like different types of GPUs in this model. So in the summary, for how Prophet solved the challenges that I said before, first of all, from the confidentiality perspective, in order to avoid releasing all the details about internal model architecture of the DNN model, we used the high-level abstracted profiling information to hide all these model details so that users can release their abstracted information. As prediction accuracy, we proposed to improve prediction accuracy, we use anchor target predictor, we use some batch size predictor. As for the compatibility, as a new type of operation that is coming out, we use some operation name cluster. So this one is about like ACE train, which is like some training time prediction. So if you have questions, so maybe I can do that in the end, maybe. It can be, yeah, okay, yeah. So this one is about ACE train. So now let's move on to ACE cost, which is about cost optimization on cloud. So previously it was not really about just for the actual cloud. We all did experiment on cloud, but it was mostly about some deep learning training with on GPUs. But now it's more like some cloud perspective. So spot instances on cloud computing. So cloud computing is really has great success. It feels like maybe it was 2006, or at that point, the AWS released its first cloud service with EC2 and S3. And one of the the biggest advantages of using cloud is the elastic building model. So people can pay whatever they use on the cloud. So for the building perspective, there are like three main building model. One is on-demand and reserved and spot instance. But on-demand instance is generally what people know about on cloud. So they pay whatever they use for a fixed price, like some VBAC of like an hour, about $3. For the reserved instance, they like some reserve, or they promise how many years, or 1 or 3 years, I'm going to use it, and they're going to get some discount. There's a reserved instance. The next one is like spot instance. It provides significant like discount up to like about 90%. But however, the instance can be interrupted or not fulfilled and due to lack of any like resources, because spot instances are provided at a very cheaper price by using some remaining instances that are not actively used at some point. So for the spot instance, there are some AWS spot instance, Azure and Google Cloud that are all provided some similar services to end users. They behave very similarly. So then now let's look at how spot instances work. So the initial version of spot instance by AWS, it adopted the bidding mechanism. So here, what bidding mechanism means is that users specify the bidding price to whenever one wants to use the spot instance. And bidding price is set by user. And there is another price called the spot price. Spot price is set by the service provider, like there is a cloud vendor. If the user's bidding price is higher than spot price, the instance is granted to a user. So based on that, and also the spot price actually changes quite very abruptly. So after spot instances become larger than a bidding price, there can be some sudden instance termination, and we call it as outbid. So because of the spot price increase, it can happen. And also, it generally happens when unused like resources, like here in the red color, if they are become sparse, they suddenly terminate all the spot instances to give a room for the general on-demand instances. And whenever that sudden interruption happens, there are like a 2-minute warning is provided. And to help users from the cloud vendors, they provide a lot of some good spot price data set. So what it contains is that it contains all the spot price advertised by that spot price vendors. And it was very good source of information because it is changing very dynamically. And based on that, analyzing that number, that spot price, one can easily see if I set spot price at this point, at this amount, and I'm the likelihood of my instance is going to be interrupted is like some above this low and high. So it was very useful information. And also there are a lot of active research has been conducted since 2009 when the spot instance was first introduced. However, in 2017, the spot instance mechanism is changed dramatically from bidding-based and new spot model that is not really well changing. So now still AWS say they are still adopting bidding-based approach, but the internal operation mechanism changed very much. So most of the previous research that was actually happened before 2017, it becomes really useless because of that internal mechanism changes. So there maybe around at the time frame, there are many other some researchers have analyzed how the price changes, the policy changes really impact that work, and they say that the price changes does not happen that often, quite as before. So which means that the price data set is really almost static. So which means that by simply looking at the spot price itself, well, users cannot really now they cannot know whether that interruption can happen or not. So there are some changes here. But however, at the point of like 2017, there was only spot price data that was the only source of information users can access in the AWS. But since then, since they have changed their internal mechanism, internal operation mechanism, they are releasing some another type of data set, the spot availability data set, the spot interruption data set. What this means is that spot availability data set, it is just for, yeah. Okay, yeah. So there, I think, let me give you example, with an example in the later slide. So there are two different new types of information also available, provided by the AWS. And actually many data set like spot price, instance availability, interruption ratio, data set is really provided by some cloud vendors like AWS, Azure, or Google Cloud. But however, there are some challenges when users want to access those data sets. So first of all the locations are very dispersed across different vendors like AWS, Azure, GCP. In its own place, they provide their own data set only. Also, the access mechanism is not really unified. So some data set provide web-based access only, and also some API, some data set provides some API or SDK, or some programmatic access is possible for some data set. And also for some data set, there are some quality limitation exist, and people can get only part of that information. They cannot get really like the large number of information. And also some of the data set provide historical information, like some previous 3 months of information, but most of the data set, they do not provide historical information, and they provide only the current information. So, but in most cases, having lots of data set, historical data set, and by analyzing it, we can do some better usage. But without that historical information, it was not possible. So to solve those challenges in the previous slide, we developed Spot Lake, which is diverse spot instance data set archive service, which was presented last year. So in this Spot Lake system, which is actually a data set archive service for various spot instance related data set in a single place. We are collecting spot price that is just for spot price, where that was like there was there like for like over 10 years. And we also added like spot placement score, as it called as SPS, which indicates the current availability of spot data set, spot instance. And it was announced by AWS in 2021. It's about 2 years. And the score has like three value, 1, 2, or 3. So which means that if the SPS score is 3 for a specific instance, it means that it is very highly likely that you are going to get some that instance successfully without some hardware interruption. 1.0 means that it's very low availability is possible and not recommended for using them. Next one is about interrupt-free score. We call it like IFS. So interrupt-free score means that how an instance has been interrupted in the previous 1 month. So we call it as like interrupt-free score is 3.0 means that in the previous months, in the previous like 30 days, the ratio of interruption frequency was less than 5%, and 2.0, which is 5 to 10% of like interruption frequency was happens in that. So which means that for both for SPS and IFS, the higher score means that the spot instance is very relatively stable comparing to any other like lower instances. So those are the data sets that we're collecting. So in our implementation, we collect those spot price SPS and IFS in a single place, and we did some analysis for that. So first of all, for different types of data set, it's spot price, spot placement score, and interrupt-free score. So let's see how difficult it was whenever we access the data set. First of all, spot price data set that is widely in use already. It is really easy. So we can just send on like AWS single command, and it will returns the previous 3 months previous record very easily. So it was relatively easy. But however, for the spot placement score, which is SPS, it was really challenging because it was imparting a lot of restriction whenever we access that data set. It has some query limitations, a number of requests that we can make, a number of query we can give. So to overcome that, we had to make a lot of some fake account to make some multiple queries, and then we could finally do that. Then I think we are running it like over a year, over now. I think it's over 1 year, and actually we are not getting banned now. We are not getting. So I think we are okay for using that. So we are using maybe about 60 account and then we are in different account sending different queries to at the same simultaneously. We are getting that information and collecting them in a single place. And we are doing it. It was very difficult for when we did it for implement for that. Next one is interrupt-free score. It was provided through web service only, and there was no way of programmatic access. But there are some other like open source implementation of Spot Info, which we could download to like web crawling those information. So using all those things, we actually build a data crawler and keeping in a single place. And we did some experiment and we did some analysis for how the data set really looks like. So first of all, we saw some temporal pattern of the spot instances. This vertical axis shows that instance classes of like T, M, A, S, various instance classes, and the x-axis shows that time since January 1st, 2022. And we can see that this left one is spot placement score, right one is interrupt-free score, and we can see that spot placement score and both of them do not show that much difference across for different times. So if they are not really lower value, they are just low. They did not change that much across different time. And one thing that we could see was that for this type of category that has some advanced accelerated computing with GPUs, and they relatively have some lower availability comparing to other general purpose general purpose computing instances. That's what we could see from that value. And then we also did analyze based on the spatial pattern of the different region, like US, Asia, and Europe. Different from temporal sparsity, temporal difference. For that spatial variations, we could see some spatial variation, which means that even for the same instance type, in the different region, we could see that in some region it was very highly available, but in some region it was not available at all, which means that whenever people generally use the cloud instance, they simply use just single region. However, based on this one, our like spatial diversity, we might need to think about using spot instances from multiple regions for higher availability. That's what we could see from those data analysis. And also, we are also curious about there are three data sets: spot price, availability, and interrupt-free score. And actually, all of three information are aiming to provide users with some information about if that spot instance is available or not. So we were curious if they are really providing similar information. So here what we did was that at the specific time, we calculate correlation of coefficient if they are really providing some similar information. And interestingly, in most cases, they do not really say the same thing. So which means that in some data set, it says that, hey, this spot instance is available. But the other data set, it says that this is not available. So there are in many cases, they are really talking about some contradicting information. And this one, it shows that, shows the information about that. So what we did was that for the SPS and IFS score, so both for SPS and IFS2 score, if they are both are high, they are all that good. And if both of them are low, the spot instance is in a very low availability. But the problem is that when SPS is high and IFS is low, also the opposite, like SPS is low and IFS is high, they are really talking about two different things. One is high, one is low. So we counted that in 24% of cases, they are like really saying in two different directions. So one is saying this is going to be highly available, this is reliable, but the other data set says this is not reliable at all. So which is really confusing to the end users. So we developed spot checker to evaluate how that real like spot instance is really reliable in the real world. So here, what we did was that for sampling a large number of like target instances, we really did some experiment about requesting spot instances and record the event of if that was available and if that was interrupted. We record all that event every 5 seconds, and we analyze the result. And then after having like, I think we have conducted experiment for like 500 instance types for like about like 24-hour time frame, and we measured for whether an instance was not fulfilled or interrupted, and we measured that based on that SPS and IFS score, when both metric is high and high, it means that they are all saying that there are very low number of not fulfilled, which means that all of them are fulfilled, and the ratio of interrupted is shown in the third column. So what we could keep finding was that whenever the SPS, the first character is SPS1, high, medium, low. The second one was IFS, interrupt-free score, high, medium, high, low, medium. And what you could see was that whenever the SPS was high, there's all of them are really fulfilled, and the interrupt ratio was very low. So what you could see was that after that experiment, SPS, that is populate score, was like really good indication of a fulfillment. And combining SPS with IFS, we could see as some auxiliary information to conject, to predict that interaction. And this was some CDF of how that different like some the value distribution of like some spot placement score and interrupt free score impact that different like some interrupt and that previous time. And in summary, what it says is that whenever both interrupt free score and SPS is high, it is much safer or much reliable than the other case of a low and low. And we could confirm that from that from real world experiment. And do that. And this one is what we are saying that if these two types of information say that if that specific type of information, SPS and IF, both of them are high, it is very most reliable. However, whenever SPS and IF imply two different information, whenever SPS is higher and IFS is lower, or the other way, IF is higher, SPS is lower, SPS should take more higher priority than IFS. That's I could see because H-L, which is SPS, IF, when the HL is always show the better result than LH, which means that SPS should be higher priority whenever we choose spot instances for schedule. And so is it really helpful for using those information? So to see that using SPS and IFS information, so if we to see that to check if it can be really helpful for the real world users application. So what we did was that we tried to model using all those different set of data set, SPS, IFS, cost saving, that is price information. We build a model. If we can predict if an instance is going to be interrupted in the next 24 hours. So by using the previous, like maybe previous 2 or 3 days data set, can we predict in the next 24 hours, what is the probability that a node is going to be interrupted? So we use a very simple random forest classifier, just to fulfill the interrupted non-fulfilled. And the last column is RF, means our very simple model. And those 3 columns means that this IF, SPS cost saving, what it means is that so this is actually prediction model. This one is simply using the data set at the time of the request. So for time t, at the time t, if one simply uses SPS as its future prediction result, this gonna be like, so accuracy is 64% and IFS is 45, and the cost saving, this is just for price. If one simply uses the cost or the price information itself, it has the very low, the lowest accuracy, which actually comply the previous result that we could see from after like 2017, the policy changes. And by combining all that data set with a very simple random forest model, we could see some higher accuracy in the spot instance reliability prediction. And then using that, now the service is currently running very well. So after gathering all that availability, internet-free, and the price information of AWS, GCP, and Azure, and that is provided at the spotLake.dps.cloud, and also with some open source implementation on GitHub. So it is going to be running. Okay, so last one is about AC inference. That is about all you can inference. So this one is about like training. It is about some cost optimization. Now let's look at this inference perspective. So in inference, so in the serverless computing part, there are many approaches and many attempts to use serverless computing for many like ML jobs, data processing job, and many other jobs. But for the end of training, it requires a high throughput. So from my perspective, it can be very challenging. So we tried to do some subarray computing-based training, and the performance was not that good in many cases. So that's what we thought about. Well, what about DNA inference? Is it good for the appropriate for the inference job? And we thought, so why not? Because DNA inference is mostly very single task with some very short period of time by using some by serving users' request. So we could see some possibility for using serverless computing for DNA inference. And then, however, there are many still challenges for when using serverless computing for limited file storage and communication pattern and CloudStars and large storage space. So there are so many research groups are just working on some expanding serverless computing's application, but for the DNA inference part, is not really not a major DNA inference platform yet as a serverless computing. So what you can do. So, but there are some large opportunities for using serverless DNA inference. So, for recently, the AWS and other vendors added new hardware support like ARM hardware, so it's for Graviton processors, which is very more cost efficient, and also that memory size is getting larger. So, for instance, in AWS, Lambda is supported up to 10 gigabytes of memory, which might be sufficient for serving some large model. And also, there are some DNA model optimization part. There are some well-known open source implementation of the graph optimizer for Onyx and Apache TVM, just for operator level compiler. And we wanted to see if we apply such new findings in the domain of serverless computing to the DNA inference, if we can get really some performance gain out of those approach. So we tried to provide some exploration space of large surface space of new hardware optimizers and inference elements. And to do that, we developed all-you-can inference, and what it does is that a user simply submit their own model just for inference, and then in that inference model, users select which option one wanted to choose, like some optimizer or some hardware, memory size. After they choose all those information, based on that information, after running all the different environments, either ARM or some Onyx or TVM or some different batch size and also different memory configuration, it simply returns output to an end user. So it's kind of some very like prototype information, prototype implementation. And so to do that, so we implement those in the various setup using some AWS services, and then we observe how it can be really effective whenever a user wants to know to get some best performing serverless computing environment. So different types of hardware for ARM and Intel, and optimizer for Onyx and TVM and vanilla with all these DNA models with some batch size and memory size. After having that, we could see that, first of all, for CNN and NLP, I think this is CNN and works for NLP, we could see that regardless of Intel and ARM, maybe there's showing really some similar performance pattern, nothing special in this place, but anyway, we could see that both models could run very well with some vanilla, Onyx, and TVM. So there, this is what we could see. So for the best performance for Intel hardware, we could see that some just for without doing any optimization shows the best performance. For ARM hardware, TVM showed the best performance in this case. And also we also analyzed that performance output by differentiating that batch sizes from 1 to 32, and we could see that comparing to Onyx and TVM that performs any some specific optimization internally, it does not show that much performance gain by applying some large batch size. However, in the vanilla case, without any optimization heuristics, it showed great performance gain as we vary that batch sizes. And next one is about some memory size and its performance. So in most cases, we could see that whenever we chose that lambda memory size, about 2 GB, it shows the best performance and cost ratio. So obviously, whenever we allocate more memory in the lambda, it shows like better performance. However, the performance gain is not really proportional to that increased memory size. And then so we could also confirm that. So in most cases, that about setting just for 2 GB has the like best performance and cost range in most models. And yeah, so this one was actually still ongoing work in our lab. So we wanted to generalize all that performance, and we just were providing some general model to guide users to set up some inference environment using serverless computing. So this is actually ongoing work in my lab. So let me conclude this talk. So this is the overview of what my research group is actually actively working on these days. So other than that, we're also working on a little bit about some edge computing and edge computing AI and inference on edge side, but they are not actually, we did not make publish yet, so I did not edit here. So maybe if we have a chance, we can chat about that also. So as a final remark, so for edge training, I talked about some training time prediction on CNN. As cost, we provide a data set how to better use spot instance, and or you can inference for DNN inference on serverless computing. But at this point of time, there are really some fundamental or just very basic algorithm that a user should apply to get the optimal environment. But in the future, or to help users better use cloud computing for the application or AI application development, all those that algorithm should be conducted by the cloud vendor or service provider or any other like middleware layer. And then users don't really have to think about, hey, what's going to be my training time on different GPUs? How can I get the most reliable spot instances to get most cost beneficial environment? All those information should be handled by some middleware in between cloud service provider and user, so that users can really focus on that core application development. So I think that's where we are aiming for the cloud computing and evolution direction in my group. Okay, yeah, I think that's all for my talk. Thank you.